to our last session for today. So Daniel Wichs from Northeastern NTT Research will tell us about spookily homomorphic encryption.
All right, great, thank you. So thanks for the introduction, and thank you for the organizers for inviting me, and also for actually figuring out how to make this work really well online. So I'm going to be talking about spookily homomorphic encryption. This is actually based on, let me see if the advanced slides work. Okay, so this is based on two works, one from Yurka with Brakai and one from Crypto 2016 with Evgeny, Shai, and Ran. So these are somewhat old works. Actually, I gave a talk about the first work at Simons 5 years ago in 2015. I spent a semester at Simons. So I gave a talk about it, and actually the second work came from a collaboration that started at Simons. I had a really great time doing that semester. It was really practice. I'm expecting that after this talk, we'll start a new collaboration. There'll be another paper. Okay, so the talk is about I'm going to focus on three different primitives. I'll start with fully homomorphic encryption, which I expect most people already know, but I'll just briefly mention it because it'll let me frame the other two. And then the focus will be on two new primitives, something called multi-key fully homomorphic encryption, which is sort of a fully homomorphic encryption in the multi-user setting when there's multi-users, and a stronger version of that, which is called spooky fully homomorphic encryption. And you'll understand why it's called spooky during the talk. So the talk focuses on these primitives, and it's roughly divided into three parts. So first I'll tell you what these primitives are, what these notions do. Then I'll tell you why you should care about them, some applications of them. And last, I'll tell you a little bit about how to construct them. So how to build them. So let's start with the what part. I'll tell you what each of these things is. So fully homomorphic encryption, again, I expect many of you already know, but it's an idea that goes back quite a long time, but we only started getting constructions recently, starting with the work of Gentry in 2009. And the idea is that we have a user as input X, and the user can encrypt this input, so generate a public key and a secret key for an encryption scheme, and encrypt the input X under the public key. So in that sense, it acts like standard public key encryption. But there's this extra amazing capability, which is that the user can take the ciphertext and send it to someone, let's say upload it to some cloud server, and then ask the cloud to compute some function, evaluate some function F over the encrypted data. So there's some additional homomorphic evaluation procedure, eval, that takes as input a function F, represented usually as a circuit, and the ciphertext C, and it outputs a new ciphertext C star.
Oh, he started already. Okay, let me push this. Sure.
Okay, so someone has their microphone on, I think. Okay, so so the eval outputs some ciphertext C star, and if you try to decrypt, if the user tries to decrypt C star with the secret key, they output F of X. So essentially, they manage to take an encryption. You can take an encryption of X and convert it into an encryption of F of X for any function F. So multi-key FHE is just an extension of this into the setting with many users. So now here we have several users that have different inputs, X1, X2, X3. And in this setting, they can each choose completely independent public keys and secret keys. So generate their own key pairs, and they're going to encrypt their data individually under their own public keys. Okay, so you get three different encryptions of these different inputs, X1, X2, and 3, under different public keys. And so using standard fully homomorphic encryption, you cannot really do anything. You can operate on each of these ciphertexts individually, but you can't really do anything that combines all these inputs. And so that's what multi-key FHE lets you do. So here there's a special procedure that lets you evaluate some function over all three, over the data encrypted by all these different ciphertexts that are encrypted under different keys, and derive some ciphertext C star. Now, I want C star to be an encryption of the output of the function of the data of F of X1 up to X3, but encryption under what key? Who can decrypt C star? And if you think about it, it shouldn't be the case that any individual user should be able to decrypt this C star, because that would break the security of the other users. So for example, if the user who has input X1 could decrypt it, then that means that she could learn something about X2 which is encrypted under a different public key. So no single user should be able to decrypt the ciphertext C star. But still, what we want is that there's a way to decrypt it given the secret keys of all the user collaboratively. So if all the users come together, they can decrypt this output ciphertext C star and recover the output of the function on the 3 inputs, on X1, X2, and X3. And actually, we want something stronger. So we want this to be durable in a very nice and easy distributed way. So actually, they don't have to run some complicated interactive protocol, but actually each user just takes their own individual secret key and computes a partial decryption of the ciphertext C star. So they compute these 3 partial decryptions, Y1, Y2, Y3, and then you can combine these to recover f of X. So there's essentially a 1-round distributed protocol for decrypting the ciphertext. Okay, so some background on multi-key FHE. This notion was actually originally proposed by Adriana, Eran, and Vinod in 2012, and they gave a construction based on the entry problem. So unfortunately, this construction did not have a nice distributed decryption procedure. There was no easy way for the parties to decrypt the final ciphertext in a simple 1-round protocol. So later, there was a construction given by Clear and McGoldrick from the basic LW problem, and they had a really nice idea. They really showed how to do this. But it was a somewhat complicated construction. It took us a long time to understand what it's doing, and there was no, they didn't talk about this distributed decryption procedure, which I should mention is actually crucial for a lot of applications. And so in a paper with Pratyay, we simplified this construction of Clear McGoldrick. We sort of gave a framework for how to understand it. And we showed that actually it's pretty easy to add this distributed decryption to this construction.
Daniel, there's a question from Alex Grillo. Is there some notion of secret sharing, namely that YI does not leak information about FX?
Yeah, there should be. Yeah. So it should be a secure distributed decryption so that no single, you need to get all the partial decryptions together to recover the output. So actually that's in some sense already implied by semantic security, because no subset of the parties should be able to figure out the output on their own. That would break the security of the party that's left out.
So Daniel, when there isn't distributed decryption, does that mean that like there's a decryption algorithm that just takes all the secret keys, or how does that work?
Right, it's some complicated algorithm that takes all the secret keys and does a complicated process to figure out the data, but there's no easy way to distribute this algorithm by, in 1 round, let's say. I mean, you could each party could just send their secret keys, but that would break their own security. So you want something, you want something that's some extra security features that you essentially, these partial decryptions don't reveal anything other than the output.
I see.
Yeah. Okay, so this is the background was known before. And then I want to get to the last notion, which is spooky fully homomorphic encryption. And so this notion might seem a little less natural, but I think it's really conceptually interesting. So someone spent some time on it. So here the setup is the same as in multi-key FHE. We still have several parties, and they all choose their own individual key pairs, and they encrypt their individual data under their individual keys. So you have encryption of X1, X2, and X3 under these 3 different public keys. Now they send the data to the cloud. So far, everything is the same as in a multi-key setting. But now, instead of asking the eval function to compute a single ciphertext, we're going to ask the eval to actually do some complicated operation on all of these 3 ciphertexts and output 3 different ciphertexts for the 3 different users. So it doesn't output one ciphertext that they all collaboratively decrypt. It computes instead 3 individual ciphertexts, 1 for each of the users. And now each of the users decrypts their own ciphertext with their own secret keys and gets some values Y1, Y2, and Y3. Okay, so we start with some inputs X1, X2, X3. We encrypt them, we run it through some process, and then produce 3 output ciphertexts that are then decrypted to get these outputs Y1, Y2, Y3. And so the question is, what kind of relationships can you achieve between the inputs that come into this process and the outputs that you derive? So you're converting encryptions of x1 to xn into encryption of y1, y2, yn. What relationships between the x's and the y's can you achieve? So one simple observation is that you cannot get signaling relationships because of the semantic security of the encryption. So what do I mean by signaling? So you can show that for any subset of the outputs, if I look at the outputs for this subset of the parties, the subset of parties capital I, they cannot depend on the inputs of the other parties that don't belong to the subset. If that happened, if that was the case, that means that somehow this subset of parties capital I can break the security of the encryptions of parties that don't belong to it, which should not happen. Okay, so you cannot signal, you cannot communicate from encryptions under one key to encryptions under a different key. Data cannot flow between, communication cannot flow between keys. On the other hand, you can achieve local relationships. So each yi can be an arbitrary function applied to the xi, and that's just by using standard fully homomorphic encryption. So we can do signaling, we can do local. Maybe if you haven't seen this before, you might think, well, that settles the whole problem. But it turns out that actually, surprisingly, there are things that are in between. There are relationships that are neither local nor signaling. And the question is, can you achieve these types of relationships? So here, let me give you an example. So for example, can I ensure, so there's in the two-party case, when n is 2, can I ensure that the outputs y1 and y2 XOR to the AND of x1 and x2? So if you think about this, so this would be like y1 and y2 are secret sharing of x1 and x2. So each one of them, each yi, might not reveal, might be independent, might just be a random value and independent of both x1 and x2. So this does not signal because each yi is just random and doesn't tell you anything about them. But if you look at the y's together, if you look at the two of them, they sum up to the AND of x1, x2, and this is not something you can do by just setting each yi as a local function of xi. Okay, so so this relationship is also called the CH-SH game, I believe, and that's been studied in quantum and has some interesting relations to quantum mechanics, which I'll talk about on the next slide. But this question was actually first asked by Dwork et al., and they asked this in a real interesting context. They actually noticed that there was a previous paper that did something very interesting, but their security proof implicitly assumed that you cannot do this. You cannot take some x1, xn and produce y1, yn that would satisfy some non-local but not signaling relationship, like let's say the relationship over here.
Daniel?
Okay, yeah.
So sorry, one clarification. So in homomorphic encryption, usually the evaluation function is publicly computable. So that means that all three parties can compute all three ciphertexts? Yeah, that's right. The function is publicly computable. So there's no difference. So if you have a single out, except for efficiency reason, so the ciphertext could be a concatenation of all three things, and you can still think of it as being a single ciphertext, the output. Well, no, so let's go back to the previous slide. So I want each party to, so the output consists of three ciphertexts, but each party outputs its own decrypts its own ciphertext. Oh, and they don't get, so they don't get to see the other input ciphertext. Yeah, they don't talk to each other. So I'm outputting three ciphertexts for three parties. They don't talk to each other, and each one locally decrypts. But the evaluation function is working on all three ciphertexts. Exactly. So it is publicly computable, but not everybody has all the inputs. Exactly. So, well, not everyone can decrypt all the outputs, right? Each ciphertext can be decrypted by just one. It's supposed to be decrypted by just one party. Mm-hmm. Thank you. So essentially, we're saying we're encrypting some x's under a vector of x's under individual public keys. And we're computing on the entire vector to get a vector of y's encrypted under the same public keys, respectively. And the question is, what relationships between the x's and the y's can we achieve? So we can do operations under each public key individually. That corresponds to these local relationships. We cannot signal. So any yi cannot contain information about xj for j not equal to I.
or any subset of yi's cannot contain information about any x's that are outside of that subset. But then the question is about these types of relationships over here that are neither local nor signaling.
No, okay, I see that. No, but sorry, can you go back to the previous slide?
Yeah.
The one with the diagram.
This
So usually when you encrypt something under a public key, you think of it as being already, protected. But here you're assuming that these ciphertexts are sent to eval through a secure channel, so that other people cannot even get to see the ciphertext.
No. So I'm not making any such. So eval is sort of there for a correctness, not a security reason. So the security property is just standard encryption security. Semantic security, okay? There's no other security property. And the functionality property that I'm requiring is the following, is that just the eval works on all the ciphertext and produces a vector of encrypted output, and now gives each output to one party who doesn't have the secret key. So the first party has their own secret key, doesn't have secret keys of others, and decrypts the first ciphertext. And that's how I generate the Y.
Okay, so the adversary gets to see everything, but for correctness, the parties should be able to compute only locally.
Exactly. Yeah, the security is just standard semantic security. Each encryption hides the data. This is so the spooky property is a correctness property. I want to ensure, or I want to generate some relationship between the outputs Y and the inputs X.
Daniel, so there's a question from the audience asking whether it is necessary for CI and CI prime to be secrets.
No, it's not. So again, the security property is standard encryption security. So the ciphertext should hide the encrypted input.
Right. Thanks.
Yeah. Okay. So the question is, with the restriction of standard encryption security, what kind of correctness property what kind of relationships between the encrypted inputs and the encrypted outputs can we generate? And in fact, this was originally asked in a question in the context of actually not wanting to generate interesting relationships. So originally this was asked because there was a very interesting word that constructed some variant of snarks that essentially made the assumption that if you do this, if you get a bunch of encrypted X's and produce a bunch of encrypted Y's, then it means that each Y can only be a local function of the corresponding X. And in some sense, not clear if that's generically true. And so we're asking that. So the question is, can you actually create some non-local relationships as well? So I just want to give a physical analogy. This is actually very related to something people study in the setting of quantum physics. So here, imagine there's two users that are on different planets that are, I don't know, light years away. They can't talk to each other because the communication will take too long to get from one to another. And now each of these people suddenly gets some input Xi and has to produce an output Yi. And the question is, what relationship between the X's and the Y's can these people, can you get? And so because they're on different planets light years away, and they cannot communicate, you can show that this relationship cannot be signaling. So Y2 cannot depend on X1 and Y1 cannot depend on X2. On the other hand, it's easy to do local relationships. So Y1 can be any function of X1, Y2 can be any function of X2. But the question is, can you do something in between these non-local but non-signaling relationships? And very surprisingly, if using the properties of quantum physics, if these parties share some quantum entanglement ahead of time, then they can actually do this. They can generate some non-local relationships, non-signaling relationships between the Y's and X's. For example, exactly the relationship I mentioned on the last slide, where the Yi's are secret shares of X1 and X2, of the AND of X1 and X2. So you can at least do this with better than trivial probability. Okay, and so Einstein thought this was a spooky fact about quantum physics, so he called it spooky, and that's why we call this in the encryption setting, call it spooky encryption. So I just want to explain the analogy a little better. So we have the physical setting, the cryptographic setting. So in the physical settings, the messages, the X's, the inputs are separated by being far apart. So the two parties can't communicate about the inputs to each other because they're too far apart. And in the cryptographic setting, the inputs are separated because they're encrypted under different keys. So the two X's are encrypted under different public keys. And therefore, you cannot send information from one public key to another public key that would violate semantic security. So, so exactly that shows that signaling strategies cannot be done in the physical settings because of communication cannot happen faster than light, and in the cryptographic setting because you violate semantic security. On the other hand, it turns out in the physical setting, it's possible to realize some non-signaling strategies via quantum entanglement. And then the question is, can you do something similar in the cryptographic setting? And that's exactly what the goal of spooky encryption is.
Daniel,
yeah.
confused about whether I should be thinking of this as like a counterexample, like, look, this thing exists, so therefore when you try to prove things, you have to consider this possibility, or is it like an actual thing that I want to use for applications?
Is there a difference? I mean, both. I'm going to talk about some applications of this, but yeah, it's also a counterexample. So people have tried to build, have tried to use the fact or rely on the fact that this cannot be done, and so this shows that you cannot rely on that.
Okay, but I might actually want to do this spooky thing. It's not just to creepy.
Yeah, yeah, that's right. So in this talk, actually, I'll show you how to do this kind of, how to get these types of spooky relationships under LWE. You can actually generate a large class of spooky relationships between the X's and the Y's. And in particular, you can get the following class of relationships. I'll call them additive function sharing spooky. So for any function f, you can make sure that the yi's are just a secret sharing and additive secret sharing of the f applied to all the inputs. So you can compute any function on the inputs and make sure that the resulting y's are secret sharing of the output of that function. Okay, and so this is one answer to Noah's question. It turns out that the spooky fully homomorphic encryption, you can think of it as a very special type of multi-key FHE with a really easy distributed decryption. So if I think of the encryptions of Y1 up to Yn as the one ciphertext, that is generated by the multi-key FHE, then it has a really easy way of decrypting it in a distributing manner where the first party just decrypts the first component and outputs Y1, the second party Y2, and so on. So the partial decryptions are just the YIs, and then the parties send them, and you just sum them up to get the output. So this is spooky FHE is in some sense just a special case of multi-key FHE with a very simple distributed decryption where the parties just locally decrypt and get a secret share of the output and just send the secret shares and sum them up. Okay, so why do I care about these? So there's a couple of different reasons. I'm only going to mention really one application, which is the two-round multi-party computation. But there are a couple of other applications very related to function secret sharing and homomorphic secret sharing. And also, as Noah mentioned, there's also gives you some interesting counterexamples. So let me just tell you about the application two-round multi-party computation. So in multi-party computation, we have several parties that have some inputs, x1, x2, and so on, and they want to compute some function on these inputs. And they do this by running a protocol where correctness says that they compute the function, and security says that nothing else is revealed except the output of the function. And the question is, how many rounds do you need to do this? So previously, there were results that showed how to do this even in constant number of rounds. But you can show that actually you need at least 2 rounds, and it wasn't clear if you could do it in exactly 2 rounds. And so with this multi-key fully homomorphic encryption, you get an incredibly simple multi-party computation protocol that works in 2 rounds. So here, each party just chooses their own public key and secret key pair and broadcasts the encryption of its input under its own public key. Then all the parties, so this is just the first round, each party just sends an encryption of its input. After that, at the end of the first round, the parties just, all the parties individually run the homomorphic evaluation algorithm and compute the ciphertext V star that encrypts the output of the function. So we can think of the eval of the homomorphic evaluation as being deterministic. So each party can just do this on their own, and they all get the same output ciphertext C star. And then in the second round, the parties run a distributed decryption protocol. So each party sends this partial decryption of C star, and then you just you use these partial decryptions to recover the output Y. So it gives you an incredibly simple format for a 2-round MPC given a multi-key FHE. And if you have a spooky encryption, you actually get something a little better. So at the end of the first round already, the parties compute an additive secret sharing of the output. So you have a 1-round MPC protocol where the parties don't get the output itself, but they get a secret sharing of the output at the end of the first round. And then the second round just consists of all the parties sending out their shares. Okay, so the last part of the talk, I'm gonna tell you how to actually do this. And so I'm gonna start by telling you about just basic fully homomorphic encryption. This will be the Gentry, Sahai, and Water scheme. I believe you already heard about it at the beginning of the workshop from Otestov, so this will be just a quick summary. And we're gonna see how to use these techniques to extend them to get both multi-key FHE and spooky FHE. Okay, so let's recall the Gentry, Sahai, and Waters fully homomorphic encryption scheme. So here, the public key is just a matrix A, and it has this format where the top n-1 rows, or all except the last row of the public key, are just uniformly random. So I'll call that matrix B. And then the last row is just an LWE sample with this matrix B. So just a random linear combination of the rows of B plus some noise. And the secret key is just this vector S, which is the linear combination. So it's actually negative S concatenated with 1. And you don't really have to remember much about this, except for this last property. So the relationship between the public key and the secret key is that if you take the secret key and multiply it by the public key, you get the small error vector E. So you get something small. And I'll just write these squiggly lines to denote small things. So I'll say the secret key times the public key is essentially 0. And I want to mention that the top part of this matrix B, you can think of that as a common public parameter. People don't need to have any trapdoors for that. So we can just generate that once and for all, and all parties can use the same. We can always use the same B when we generate fresh public keys and secret keys. Okay, so to encrypt some input X, some bit X under this public key, the encryption algorithm does the following. It just takes the public key A, this A matrix, and re-randomizes it by multiplying it on the right by a square matrix with short entries, let's say just random 0, 1 entries. And then we add the bit X times some gadget matrix G. And I think you already heard about the gadget matrix, but I'll mention more what we need from that in a little bit. Okay, so this is the ciphertext. And again, you don't really need to remember much about this. You just need to remember the main property, which is that if you take the secret key and multiply it by the ciphertext, you get the bit X that was encrypted times the secret key times the gadget matrix G. Okay, so that's the encryption procedure. And this actually also automatically gives us a way to decrypt, because if X is 0, then this whole vector will be very close to 0. And if X is 1, then this vector will have some large entries. So by checking if this vector is close to 0 or not, you can recover X. So the security of the scheme is really easy to show. It follows in one line here. So if I give you the public key A and a ciphertext AR plus XG, this is some encryption of X. Then by LWE, A is indistinguishable from a random matrix, U. So this looks like U and U times R plus XG. And by the leftover hash lemma, U times R looks like a random and independent value. So if I give you the public key and ciphertext, they just look like random and independent, two random independent matrices. Okay, so how do we do the homomorphic evaluation? That's really the interesting part. So assume I have two ciphertexts, C1 and C2, that encrypt bits X1 and X2 respectively. So by the way, it turns out to compute, to evaluate any circuit on encrypted data, it's sufficient if I can do addition and multiplication. Those are complete operations. If I can encrypt and multiply bits, I can evaluate any circuit. So here are two ciphertexts that encrypt some bits x1 and x2. And I want to derive ciphertext that encrypts the sum of the bits as well as the product of the bits. So addition is really easy. I'm just going to add the ciphertext. And you can see that the same property holds if I the resulting ciphertext just encrypts the sum of the bits. If I multiply it by the secret key on the left, I get x1 plus x2 times t times g, which was the property I wanted. What about multiplication? It's actually only slightly harder. And so I would expect that I would just multiply the ciphertexts together. That doesn't really work. They're not even the right dimension. But it's almost the same thing. I just multiply C1 by some function of C2. I'm going to call this function the G inverse function. So G inverse is a function such that G times G inverse of C is equal to C. It's not really a matrix inverse because G is not a square matrix, but it outputs a value where, so G inverse of C outputs some value such if I multiply on the left by G, I get C. And also G inverse of C should have small entries. That's actually crucial. Okay, so and we have such a gadget matrix, just a public, we have such a gadget matrix G, and this for which such a function G inverse exists and is easy to compute. Okay, so with this way of multiplying the ciphertext that I get, you can do a simple calculation. You can check that it actually does correctly encrypt the product of the two bits, x1 times x2 dg. Okay, so this lets me do addition and multiplication. Therefore, I can evaluate any circuit on encrypted data. You need to keep in mind that as I'm doing these operations, there's some noise in the ciphertext that I'm hiding, and this noise grows as you're doing computation on the ciphertext. And so in some sense, you have to choose your parameters. You have to choose your modulus to be large enough to handle the big noise that you get at the output level. So the efficiency here degrades with the depth of the circuit D, but it turns out you can fix this via bootstrapping. So this is so far basic fully homomorphic encryption, and now we're going to see how to use this, how to adapt this to get multi-key fully homomorphic encryption. So we're going to try to stay as close to this GSW encryption scheme as possible, and just going to create a multi-key version of it. So here we're imagining a scenario where we have n parties, and these parties generate independent key pairs, public and secret keys of the GSW encryption scheme, except that they're going to use, when they generate the public keys, they're going to reuse the same matrix B. So we're thinking of that matrix B as some common public parameter or common reference string that all parties use. Okay. So in this scenario, each party I has some secret key Ti, and its data is encrypted with respect to the secret key. I'm going to define an expanded secret key, which just consists of the concatenation of all the secret keys of all the parties. So I'm just going to concatenate them together and call that vector T hat, and I'm going to call that the expanded secret key. And my goal will be to take any ciphertext that an individual party I encrypts and somehow convert it into a ciphertext that's valid, that decrypts correctly under this expanded secret key. I'm going to call that the expanded multi-key ciphertext. So what I want is to take some ciphertext C that is a good encryption of X under the secret key of party I, so satisfies this property, and convert it into an expanded ciphertext, which is a good encryption of the same bit X under the expanded secret key T hat. And everything here grows, so also the gadget matrix G will grow. We're going to get this expanded gadget matrix, but it turns out the expanded gadget matrix has the same properties as the basic gadget matrix, so this is okay. And I claim if I can do this, I'm done. I'm almost done. So if I can convert any individual party ciphertext into this expanded ciphertext, then to do homomorphic computation on ciphertext encrypted by many parties, I'm just going to take all those individual ciphertexts, convert them all into this expanded format, convert them into expanded ciphertext under the expanded key T hat. And now all the ciphertexts are under the same secret key T hat, so I can perform homomorphic operations on them the same way I would on basic GSW ciphertext. So just the dimensions grow, but otherwise everything else is exactly the same. So I can then compute on all these ciphertexts because on all these expanded ciphertexts because they're all under the same key, namely the expanded key T hat. So the hard part is how to do this step, how to convert a ciphertext of one party into this expanded multi-key ciphertext under the keys, under the expanded key that concatenates the keys of all the parties. So let's do this for n equals to 2 parties, and I claim everything else extends naturally to more than 2 parties as well. So once you see how to do it for 2 parties, it's sort of the same thing for more. Okay, so here we have 2 different public keys and secret keys for 2 parties, 1 and 2. So we have public key 1, A1, and secret key 1, public key 2, and secret key 2. And we have some encryption, party 1 encryption of an input X. So this is the ciphertext of party 1, which encrypts some input X. And our goal will be to convert that into this expanded ciphertext under the expanded key of both party 1 and 2. So we're not going to be able to do that as is. We're going to need some additional helper info that party 1 will release. So the encryption of party 1 of each, the individual encryption of each party is not going to just be GSW. It's going to be GSW plus some additional helper data that is TBD. I'll tell you in a little bit what that needs to be. Okay. So, so we take the ciphertext of party 1. We know that satisfies this property. If you try to decrypt it, so if you multiply it on the left by the secret key of party 1, you get XT1G. So what happens if you try to decrypt the ciphertext of party 1 with the secret key of party 2? That seems like a really bad idea. I mean, if the scheme is secure, this really shouldn't work. If you've got the right output, if you manage to recover X, that would break the security of the scheme, that would break LWE, that would break lattice assumptions, and we'd all have to go home. So let's see what happens. Hopefully it won't work. If you follow these equations, well, it actually almost works. You actually get XT2G, but you also get some additional blinding factor, which is just B1 minus B2. So these are the 2 public key components of parties 1 and 2 subtracted from each other times R, where R was the encryption randomness. So essentially, if you try to decrypt parties 1 ciphertext with secret key 2, you get the right output, but it's blinded by this value over here. So here's the idea. So this gives us an idea for how to create this expanded ciphertext. So we have this ciphertext C of party 1 that decrypts correctly under its own key, and we want to convert it into ciphertext that decrypts correctly under the concatenation of the keys. And so here's the idea how to do that. We're going to define this expanded ciphertext C hat in this way. So where I'll tell you how to choose the matrix D in a second. So I'll call that the unmasked term because it's going to try to cancel out this value over here. Okay, so if I define C hat this way, that when I decrypt it by the expanded secret key, I get almost what I want. So I get XT1G on the left, and I want to get XT2G on the right, but I'm going to get the blind term over here plus T1D. So I want to choose D carefully so that T1D is equal to B2 minus B1R, that they cancel out. Okay, so now, again, what this shows is that in order to be able to use the encryption of party 1, the ciphertext of party 1, and expand it into this expanded ciphertext, my goal is to somehow define to have party 1 send some additional helper info that would let me compute a matrix D that satisfies this property. So I need to show you how to do that. That's the last step. So again, so I need to show you how party one can give some additional helper info that will let us compute this matrix D that satisfies this property here. And here's the idea. The idea is that the helper info is just going to consist of GSW encryptions of the randomness of each bit of the randomness used to create the GSW ciphertext of party one. So remember, party one generated, sorry, I'm going to go back one slide. So party one generated this GSW ciphertext of its bit X. And then we're going to take this randomness R that it used to encrypt it, and we're going to take that and we're going to encrypt it again under the same, using the same scheme. So we're going to create many ciphertexts for each bit of this randomness. So these ciphertexts satisfy this property. And it turns out that by doing a fairly simple homomorphic operation on these ciphertexts, we can derive this matrix D that satisfies the property we wanted. So in particular, you can think of this as a homomorphic computation that has encryptions of the randomness R, and it knows the values, the public keys B1 and B2 in the clear, and homomorphically computes an encryption of B2 minus B1 times R. Now, it's not quite this is not quite right, because here this ciphertext decrypts the vector. When it decrypts, you're missing the matrix G, so it's not exactly a standard homomorphic computation on GSW ciphertext, but it turns out this is something you can do pretty easily with the GSW scheme, and so that's really what solves the entire problem. Okay, so so sorry that this was a little bit of messy algebra, but once we do this, we're really done, and we're able to take individual ciphertexts under the GSW scheme and convert them into these expanded ciphertexts. Then we can do all of the homomorphic operation on the expanded ciphertext, and we get an encryption of the output under the concatenation of the keys. So, so we're done. We're able to compute an encryption of the output under the concatenation of the key. Now let's see how to do a distributed decryption. So again, we have this expanded secret key, which is just the concatenation of all the individual secret keys. And we have this expanded ciphertext we had that decrypts the output in this case, but some value X, and satisfies this property. So now we want to come up with a way to decrypt the ciphertext in a very simple one-round distributed manner, where parties don't reveal information about their secret key other than just the output, other than the value that the ciphertext encrypts.
Daniel, there's a question from the audience. Roughly speaking, does the party one somehow need to know party's two identity to compute the ciphertext correctly? Because it looks like party one needs to know B2.
Good. No, it does not. So let's go back here. I guess I have all these marked state. So party one is just computing its encryption C of the bit X that is under GSW. So it has nothing to do with B2. And it's also outputting this helper info. So the helper info is just encryptions of the randomness that it used to compute the GSW encryption of X under its own public key. So again, here you don't know anything about B2. Where B2 does come in is that once you have the helper info, you can, and once you have the helper info, you want to use it to take this encryption under party one key and expand it into this expanded ciphertext. So there, at that point, you do know the identity of party two. Okay, so that's when you know B2, and you can compute this matrix D, which depends on B2, and that's going to let you generate the expanded ciphertext. So again, parties are encrypting their data individually. Once everyone encrypts and you have all the different ciphertexts, then you can expand them together into an expanded ciphertext under all the keys. Here, I'm assuming you know all the public keys and all the ciphertexts at this point. Okay, so let's go back to how to do distributed decryption. So again, we have this expanded ciphertext, which is this big matrix, and we know that it satisfies this property. We take the expanded ciphertext multiplied by the expanded key, you get the output times T times G. So the first step is going to be, well, I don't want to have this T in the decryption. I don't want to do a distributed decryption where I recover X times, where I recover this whole thing, because that would reveal something about all the secret keys T had, and that would be bad. So I want to somehow get rid of T hat in there. And that's an easy step. I'm just going to multiply this expanded ciphertext by G inverse of W, where W is just the all zero vector, except for a Q over 2 in the last component. And what that essentially does is that I get a vector C hat, I get this compressed ciphertext C hat, such that if I multiply the compressed ciphertext by, if I take the inner product of the compressed ciphertext and the expanded key, I just get X times Q over 2. So this relies on the fact that T hat has a 1 in the very last component, so T hat times W is just Q over 2. Inner product T hat and W is just Q over 2. Okay, so now I compress down this big expanded ciphertext into some long vector C hat, and my entire decryption procedure just consists of taking an inner product of this ciphertext C hat with the concatenation of all the secret keys. So that's something I can do in an easy distributed manner. In fact, just the first party can just take an inner product of its secret key with the first part of the ciphertext C1, the second party with the second part, and so on. So essentially, each party is just going to take an inner product of its secret key with the corresponding component of this ciphertext C hat. And then we're just going to take all of these YIs and sum them, and we get something close to X times Q over 2. So by rounding, we recover the output bit. Okay, so this is the distributed decryption procedure. Incredibly simple. It's just an inner product. Each party just does an inner product of its secret key with part of the ciphertext. So now if we want to go to spooky encryption, actually, if you look at the last slide, we see we're almost there. The output of this encryption was, so this ciphertext C hat, which was the result of the homomorphic evaluation, actually does consist of an individual ciphertext. And essentially what we're doing is just decrypting them, just taking the inner product and summing up. But there is a little bit of a discrepancy. So let's see what the discrepancy is. It seems like we're almost there, but not quite. And the problem is that if I think of a decryption operation on in the single key setting, at least on these compressed ciphertexts, would be to do an inner product followed by a rounding operation. That gives you the encrypted value X. Whereas in the multi-key setting, so if I want to decrypt the multi-key ciphertext, I need to do a bunch of these, I need to do the inner product on all of the components, sum them up, and then round. Okay, so to decrypt the multi-key ciphertext, I sum up these partial decryptions and then round them. Whereas in spooky encryption, we want to sum up individual decryptions and get X. So what we want is actually just the order of the rounding and the sum being reversed. So in spooky encryption, we want parties to individually decrypt their data, and then just have that be an additive secret sharing of the encrypted value. So we want to first round and then sum. That's actually the entire difference. Are we doing summing and then rounding, or rounding and then summing? So unfortunately, these two operations are not the same in general, but it turns out that they are the same in the two-party case, when n is equal to 2. So it turns out that if you sum up two values and then round them, this is the same as rounding and summing up the values. Right, so this only works, I should have mentioned, this only works if the sum of the values is either close to Q over 2 or 0. So if I have two values that are either close to Q over 2 or 0, then these two operations are equivalent. They both give you, so summing and rounding is the same as rounding and summing. And the proof is a simple proof by picture. So if I have two values that are very close to 0, then that means they're either very close together. So I have two values whose sum is so I have two values that are either very close together, in which case if I round, then I get the same value, so I also sum up to 0. I have two values that are on the opposite end of the circle, so I have something like one value here and one value here, and then chances are if I round, they also they round to opposite bits. Okay, so it turns out this works for 2, but it does not work for more than 2, for n equals to more than 2. So, so the good news is we get spooky fully homomorphic encryption, but only for 2 parties, not for arbitrary number of parties. So it turns out that there's one more trick to go from 2-party spooky encryption to many-party spooky encryption. And the trick is very similar to the GMW multi-party computation. So let me show you what this trick is. So it's a generic trick. Assume I have a fully homomorphic encryption that lets me do spooky operations on 2 ciphertexts. So I can take some encryptions of x1, encryptions of x2, and come up with an encryption of y1 and y2, which are secret sharing of, let's say, x1 times x2. I claim that's enough to then do arbitrary additively spooky relations. So here's the idea. Assume I want, so I'm starting with encryptions of some inputs, x1 up to xn, and my goal is to come up with encryptions of outputs, y1, yn, such that the sum of yi is an arbitrary function evaluated on x1 up to xn. Okay, so this is my goal, to create a spooking FHE for n parties. And the idea is to follow the GMW MPC approach. So we're going to start with an invariant where for each wire in the circuit, I have encryptions of some values W, which are the secret shares of the values that go across the circuit. So it's like GMW except under encryption. Okay, and so this invariant can be satisfied for the inputs because here I actually have just an encryption under public key I of the input xi, so I can just encrypt zeros for all the other parties, and I have encryptions of a bunch of values that sum up to the input x. Okay, and we're going to show how to preserve this invariant. So if I'm an addition gate, then I'm just going to use single key homomorphism. I'm just going to use the fact that this encryption scheme is just additively homomorphic for in the single key setting. So I'm just going to take all these encryptions of all these wire values and add them up component-wise. For a multiplication gate, it's a little more complicated, but I'm going to just rely on the fact that I have 2-party spooky operations. So I can take inputs of 2 parties and come up with 2 encryptions that secret share, that are encryption of the added secret sharing of the product of these inputs. So in particular, I have encryptions of some values A1 up to AN that sum up to A. I have encryptions of values B1 up to BN that sum up to B. And I want to come up with encryptions and I'm trying to come up with encryptions of a secret sharing of the product of A times B. So here's the way to do this. I'm just going to use the 2-party spooky operation to come up with encryptions of some D and E values that sum up to any product AI times BJ. Okay, and I'm just going to sum up the encryptions of this form of any party I to get these encryptions of CI, and now the CIs add up to A times B. So this is the, so in the GMW setting, we used OT to do this type of multiplication, whereas here we're using this additively spooky homomorphism to be able to implement this operation. But otherwise, it's really the same idea as GMW MPC. Okay, so that's really all I wanted to show you. So that shows you how to get spooky homomorphic encryption. So these works are somewhat old, and there's been some real interesting progress since then. So here's a bit of an epilogue to this. So one question you can ask is, can you do 2-round multi-party computation without multi-key FHE? So multi-key FHE also has these compactness requirements that don't seem inherent for multi-party computation. I mean, they're nice to have if you want to have multi-party computation with low communication complexity. But if I just care about doing 2-round MPC, it doesn't seem that multi-key FHE is inherent. And indeed, it was shown that it's not inherent that you can do 2-round MPC without doing multi-key FHE. there's a really beautiful work by Garg and Srinivasan and Ben-Hamoud and Lin that show how to use 2-round OT to get 2-round MPC. And you can do this even in the plain model without a CRS, without a common reference string. Another question you can have is if you can construct multi-key FHE in the plain model. So if you remember in our construction, we did actually, so the parties chose their public key, secret keys independently, except that they had this common shared matrix B that they all used. We said that there was some common parameter or a common reference string that all the parties needed to use in order to be able to compute on the ciphertext of all these parties together. And it wasn't clear if you could get rid of it. So there's a really very recent beautiful work that shows how to get rid of this, how to construct multi-key FHE in the plain model. Unfortunately, not from LWE directly, but from some combination of NTRU and LWE. And so a couple of open questions that are left. So first, obvious open question is, can you get multi-key FHE in the plain model from LWE alone without requiring the NTRU assumption? Another one is, if I wanted to get non-compact multi-key FHE, can I do that without LWE? So if you want non-compact FHE, it's trivial. You just concatenate the ciphertext. The only interesting aspect of fully homomorphic encryption is compactness. But when it comes to multi-key fully homomorphic encryption, even a non-compact version would be interesting. For example, it would give you a 2-round MPC. So I don't think the 2-round MPC papers actually solve this problem directly. They don't give you something that has exactly the format of multi-key FHE. So I think it's still an interesting question, even though we already know how to do 2-round MPC from other assumptions like DDH. It's an interesting open question to really get something that would have the format of multi-key FHE, but a non-compact one from things like DDH. And the last question is, can you do this where the complexity of the evaluation procedure does not scale with the number of parties? So here, in our case, when we computed the expanded ciphertext, the expanded ciphertext were actually quite large. If there are n parties, the expanded ciphertext will start size at least n squared. And then we have to compute the circuit on these expanded ciphertexts. So the complexity of the evaluation procedure was proportional to the circuit size times n squared. And it's an interesting question if you can get rid of this. So I mentioned there's some work that actually does get rid of this, but I believe there's some other deficiencies. So I think it's still an interesting question to completely get rid of this and just get circuit size times security parameter. And the last open question is, well, we talked about getting spooky homomorphic encryption. Can you get spooky-free homomorphic encryption? Can you get a homomorphic encryption scheme that's guaranteed to not allow any spooky relationships? And that would be very interesting for constructing things like snarks, getting rid of, so it will actually be an interesting security property to ensure that you cannot generate spooky relationships. So it seems to be hard. I think there's some black box separation results, but it's still an interesting open problem to think about that more. And all right, so that's where I'd like to conclude. Thank you.
So we have time for a few questions, if there are any.
Yeah, Daniel, can I ask you some question about your open problems?
Sure.
Yeah, so one question is that there are like recently 3 papers you probably have seen on the ePrint about doing 2-round MPC with reusable first message.
Yeah.
They can build them from, say, bilinear map or DDH. Does that solve your second open question? Or if not, then what is the additional property you want from the non-compact multi-key FHE?
Yeah, I think that would solve the open question. So I have to be honest, I haven't actually had a chance to read those papers yet. So I wasn't sure. I thought I saw that they did rely on LWE, but they also, there's new papers that also did on DDH.
One paper did on DDH, another paper did on bilinear map, and then the difference, the paper relying on DDH has the parameter will depend on the number of parties. The paper did from bilinear map, the parameter would not depend on the number of parties.
Mm-hmm.
What do you mean by parameter?
Parameter in the sense that you have to know the number of parties.
Ah, okay, I see.
Yeah, before you set up. So the parameter scales with number of parties exponentially. Oh no,
Exponentially.
polynomially.
Okay. Uh-huh.
And the other question is about the spooky free, like homomorphic encryption, and like, can you say a little bit about its relation with non-malleable encryption?
So non-malleable encryption is spooky free. That's great, but I want spooky free homomorphic encryption. So I want to be able to do individual. I want it to be homomorphic in the single user setting. So I want to be able to do local relations, like, but I don't want to be able to do. I want to prevent doing creating spooky relations.
I see. Okay, that makes sense. Thank you.
Mm-hmm.
We have a few more questions, but maybe we can take them offline. Daniel, maybe you can stick around and answer Q&A.
Sure, we'd be happy to.
Okay, great. All right, so let's thank all the speakers for today. You can stick around for Q&A to read the Q&A, and we continue tomorrow, same time with our quantum talks. Thanks again, everyone.